Section 1.8 is about inverse functions. And here's our definition. F of x and g of x, f of x and g of x are inverse functions if f of g of x, the composite, equals x, and the reverse composite, g of f of x, also equals x. So if g of x is called the inverse of f of x, we call g of x f inverse, and this is the notation that we use to show an inverse function. It's a superscript of a -1. It is not a power. It's not f to the -1 power. It is a superscript. Therefore, if g of x is the inverse, and we can call g of x f inverse, then we can rewrite it like this: f of f inverse of x, that would be this rewritten with the inverse notation, should equal x, and conversely g of f of x, or f inverse of f of x, should equal x. This is the function notation. We'll go over it together in class, but take a look. It is in your textbook, and this is the notation we'll be using to find inverse functions. So if we want to show that two functions are inverses of each other, we're not sure yet whether or not f of x and g of x are inverses. So we're going to just call this g of x. If we prove that they are inverses, then I can call this f inverse of x. So let's first start with f of g of x. That would be f of x minus 2. And putting x minus 2 into x for the f of x function, we will get x minus 2 plus 2, which equals x. Using the opposite composite, we will be taking g of my f of x function, which would mean plugging x plus 2 in place of x in g of x, x plus 2 minus 2, which is also x. Therefore, f of x and g of x are inverses, and we can call g of x f inverse of x. Go ahead and try this one. The one on the right would be more clear if we wrote it this way. So go ahead and try to do f of g of x and then g of f of x, and then come back to the video. So f of g of x is f of x minus 2 over 3. Plugging that into my f function, that's 3 times x minus 2 over 2 plus 2. That's, well, let's see what the easiest way is to do this. We can try 3x minus 6, both divided by 2, plus 2. And you can see that this is not going to simplify to just x. So these two functions, oh, I'm sorry, over 3. There we go. Now we're looking better. I was wondering why that wasn't working. So that becomes x minus 2 plus 2, which is an inverse. All right, now that I got my act together here, we'll try g of 3x plus 2, which would be 3x plus 2 minus 2 over 3. That would be 3x over 3, which equals x. So you can see that both of these functions do simplify to a simple x. Therefore, f of x and g of x are inverses of each other. And again, we can call g of x f inverse of x. So this is how we work it if we are given two functions and asked to determine whether or not they are inverses. We do the composite of f of g of x and then the composite of g of f of x. If both of those simplify to x, we can say that these two functions are in fact inverses of each other. If you take a look at the chart on page 235, this shows the second example that we just did, and you can see that if we start with our f function going from left to right, our f function says that we start with x, we multiply it by 3, and then we add 2. That's what this is telling me to do. It's saying take x times 3 and add 2. If we come back the other way, if we subtract 2 and then divide by 3, which is taking our function and subtracting 2 and dividing by 3, you can see that that is our inverse function. It's doing the order of operations in the opposite order, and that's my f inverse. My inverse says take whatever I have, subtract 2, divide by 3. So you can see that this was the g of x that we used. Okay? So on the bottom of 235, it does talk about the steps to find the inverse. So now instead of being given two functions and having to determine whether or not they are inverses, I'm given one function and I want to find the inverse. So you can see that step 1 on page 235 again says to replace f of x with y. So I'm going to rewrite this as y equals 2x minus 5. Step 2 says to reverse or switch the position of x and y in the function. The third step says I'm going to solve for y, so in this case, add 5 and then divide by 2. And so my final inverse is y equals x plus 5 over 2. And then to write that in inverse function notation, f inverse of x equals x plus 5 over 2. And that's the inverse. And again, you can see that the original function took whatever my function value was, multiplied by 2 and subtracted 5. The inverse adds 5 and then divides by 2. It does the inverse operation in reverse order. So this was a little different. The last step, we were given two different functions and asked to determine if they were inverses. And now we are asked to, given a single function, find the inverse to go with it. I've got a couple more examples for you to try here. So I'll put them up, stop the video, and try to find the inverse of these two following the steps we just did. Okay, so let's try this one first. Y equals x cubed plus 1. So switching x and y, subtract 1, and take the cube root. So my f inverse is the cube root of x minus 1. Looking at this example, again, replacing f of x with y so that I can switch my x and y positions. Subtract 4, multiply both sides by y, and then, I'm running out of room, and then divide by x minus 4. And that's the f inverse for the second function. Okay? So, if you found those successful, you're doing very well. Take a look at these examples if you need to further. All right, the horizontal line test and one-to-one functions. Horizontal line test is just what it sounds like. A one-to-one function is a function where no two different ordered pairs have the same second component. Only one-to-one functions have an inverse function. This means that not only does every x have a unique y, but there cannot be two with the same second component. This is not a one-to-one function. This would not have an inverse because, let's look at it again. If I do the horizontal line test, it does not pass. Any function that does not pass the horizontal line test does not have an inverse function. Now, let's continue on for a bit here. The graphs of a function and its inverse are reflections on the line y equals x. Let's look at our very first, very simple example. We had f of x equals x plus 2, and f inverse of x equals x minus 2. If I graph f of x, I went up 2, and I had a slope of 1, so it looks something like this. Then if I graph f inverse of x, I go to negative 2, and it has a function of up 1 and to the right 1, and it looks something like this. Now, this is a very, very simple function, but hopefully we can see that if I draw in the line y equals x, these two are reflections on either side of it. Let's look at one that gives us a little bit better picture of how this works. Let's look at f of x equals 3x plus 2, and our f inverse of x, oops, let me get a darker color. F inverse of x, we originally wrote it as x minus 2 over 3, but I'm going to rewrite that as negative 2, whoops, excuse me. I'm going to rewrite that as 1/3 x minus 2/3. That makes it a little bit easier to do as a linear equation. So here is my graph. Let's graph the first one. That's the color I used. Up 2 with a slope of 3. And so my line looks something like this. This line in the burgundy, I go down to negative 2/3 and I do a slope of up 1 and to the right 3. And that's my f inverse of x. If I draw my third line, my y equals x, let's see, I'll try orange. If I graph this line, we should be able to see that my first function and my inverse are reflections around the line y equals x. In other words, if I folded the paper along that line y equals x, I would have my f of x and my f inverse of x laying on top of each other. So let's go back to that example I had of the parabola. If I take this function and rotate it around the line y equals x, I will get a graph that looks like this. This is not a function. Therefore, since my original f of x does not pass the horizontal line test, when I flip it over the line x equals y, it will not pass the vertical test. So we have to pass the horizontal line test for a function to also have an inverse function. So let's take a look at this function, the square root of x minus 4. We should know that when we graph this, I'm going to do a parent function real quick. This would be the square root of x. When I do minus 4 inside, that means I'm going to the right 4. So 1, 2, 3, 4. This would be my function for f of x. Okay? Now, what would f inverse x be? Well, let's do it algebraically first. Y equals the square root of x minus 4. Switch them around. Square both sides, and we get x squared plus 4 equals y. Well, if I graph that, that is up 4, and it's a parabola. Now, do these look like they are flips on this line? I don't think so. So here's what we have to do. We have to be very careful of domain. So the domain of this graph is that x must be greater than or equal to 4, and the range is that y must be greater than or equal to 0. When I go to my inverse function, since I switched my x and my y, now my domain is that x must be greater than or equal to 0, and that y must be greater than or equal to 4. And you can see that this first restriction, by flipping my x and y, means that this portion of the graph will not be used for my inverse. So my inverse is y equals x squared plus 4 when x is greater than or equal to 0. And we have to add that to our definition for our inverse. So you can see that the x and the y switched position for the equation, and the x and the y switched position for my domain and range. As a matter of fact, in order to get an inverse function, all we really have to do is switch x, y in a table. Let's look at that with this example. I have both of my functions written here. For f of x, if I plug in x equals 4, y is 0. If I plug in 5, f of x is 1. If I plug in 8, f of x is 2. Take a look at my inverse, and look what happens. When x is 1, I get 5. When x is 2, I get 8. When x is 0, I should have done that first, I get 4. Do you see how the order pairs have all switched position? 4, 0 became 0, 4. 5, 1 became 1, 5. 8, 2 became 2, 8. So literally, an inverse function is simply a function where the x and y have just literally switched position. So one way to graph these is to graph the original function. Just switch all your x, y's and plot them, and you'll get the inverse. Remember to watch your domain and to keep track of what you need to do when you flip the domain and range. Okay, and that's what I just said. You can graph inverses by just flipping the x and y values in your table, and that's the end of this section.